Hello. In the last video, I began to introduce the theory of statistical mechanics. I discussed how a system can be in one of many different microstates, and how each of these microstates constitutes a set of values for the position and momentum of all the particles in the system. I then introduced the principle of equal a priori probabilities, which states that any system in equilibrium is equally likely to be any one of the accessible microstates. Over the next few videos, we are going to take this idea forward, and central to this is going to be the notion of information. The information is a functional that depends on the probability distribution. In general, the information is given the symbol I. The P inside the bracket here represents the fact that the information is a functional of a probability function. To be clear what I mean by this word here, you have no doubt learned that a function is a mathematical object that takes in a scalar, or some small set of scalars, and then returns a scalar, as shown here. A functional does a similar thing, except instead of taking in a scalar, it takes as input a function. It then returns a scalar, which it calculates from the function. Having cleared that up then, we will thus define a scalar-valued quantity I, the information contained in a probability distribution, and require this quantity to have four properties. The first of these properties is that the information will depend only on the probability distribution, which is uncontroversial. The second requirement of this quantity is that the uniform distribution contains the minimum amount of information. This makes a lot of sense too. If I tell you that one of the following n things will happen, and tell you that they are all equally likely to happen, then I am obviously telling you less than if I told you one of the following n things will happen, but this particular thing is the most likely. In other words, I'm giving you less information. The next of our four requirements on the information is equally uncontroversial. We state that if we enhance the sample space with impossible events, then the information will not increase. This is also rather intuitive if you think about it a little. If I tell you that one of these n plus 2 things will happen, but the last two will definitely not happen, then I could give you the same amount of information by telling you that one of these n things will happen. In fact, by making the first statement, I've made myself look a bit weird. You would probably ask yourself why I even mention the two things that definitely wouldn't happen. The last of our requirements is the most difficult one. We require that our scalar quantity, the information, is additive. This makes sense linguistically. If I tell you two things about what might happen, you obviously have more information than if I tell you just one thing. However, it is very difficult to explain in words why the information would be additive. As always in mathematics, we need to be a bit more precise here than I've been with the sort of assertions I have made to justify the other axioms of information that I've discussed on this slide. I will come back to that in a moment though. Before we do so, let's prove the following statement using the properties of the information that I've just introduced. I want to prove that the information I in a uniform probability distribution P decreases monotonically with the size of the sample space. Let's just quickly define a few terms here to make sure we're on the same page. Firstly, let's look at the word sample space. If we have a probability distribution, then that implies we are doing an experiment and that there are a number of possible outcomes to our experiment. We call the set of all possible outcomes the sample space. As our probability distribution is uniform, all of these various outcomes are equally likely to occur when we do the experiment. Only one of them will in practice occur, but we cannot possibly know which before we do the experiment. When we talk of increasing the size of the sample space, we are thus talking about increasing the number of outcomes that our experiment could have. I next want to define what we mean when we state that the information decreases monotonically. This basically means that as the number of elements in the sample space increases, the information decreases without ever increasing. We introduced this word monotonically in mathematics because we want to be precise about what we mean. A function can have a general trend to decrease, but it might have local points, say in going from 3 to 4, where it increases briefly. To be clear, this sort of thing is not allowed for our information functional. Whenever we increase the size of the sample space, the amount of information that we have decreases. This statement makes sense intuitively. If I tell you that one of n possible things will happen, I have obviously given you less information than if I told you that one of n minus 1 things would possibly happen. With the proposition we are proving clear, let's now prove it. We start by introducing a uniform probability distribution P with n possible outcomes. In other words, P is a probability distribution for an experiment with n possible outcomes that are all equally likely. We now enhance the sample space by adding an impossible event to this probability distribution. This gives us a new probability distribution, P prime, that tells us that all the outcomes for the experiment underlying the original probability distribution P are equally likely, but that there is one further outcome that will never happen. We know that this additional impossible event has no effect on the value of the information, from our third axiom, and we therefore know that the value of the information functional for the distribution P prime is the same as that for our original probability distribution P. Let's now introduce a third probability distribution Q. This will be a uniform probability distribution with n plus 1 possible outcomes. In other words, Q is a probability distribution for an experiment with n plus 1 outcomes that are all equally likely to occur. I of Q is the information contained in this probability distribution, and by one of the axioms that we just introduced, this is the minimum amount of information that you can have for a probability distribution for any with n plus 1 events in the sample space. Because we know that a uniform distribution always gives us the minimum amount of information. We have another probability distribution for an experiment with n plus 1 in the sample space, though, P prime. This probability distribution has a sample space with one impossible event. The value of the information for the probability distribution P prime must therefore be greater than the value of the information for the probability distribution Q, as the probability distribution for P prime is not uniform. We then further note that the information for P prime was the same as the information for P. We have thus proved our proposition. The information I in a uniform probability distribution P decreases monotonically with the size of the sample space. Let's now look again at this property of additivity and ask ourselves the following question. Let's suppose we have two uniform and independent probability distributions P and Q. P has a sample space with m outcomes, whilst Q has a sample space with n possible outcomes. What information is contained in the joint distribution for these two variables? Well, as always, let's consider the meaning of the question first. A way that I like to do this is to consider graphical representation of the facts in the question. The representation that I'm going to draw is a Venn diagram, and this is going to look something like this. The columns in this figure that are labelled 1 through 5 represent the various possible outcomes that are in the sample space for the probability distribution P. There are m possible outcomes in P, and thus in drawing my diagram I have set m equal to 5. If you want, we can imagine the sample space we have drawn here as a target, and that there is a person shooting at this target. Hitting in different columns gives them scores of 1 through 5. Our probability distribution in this scenario tells us the probability that we will get these different scores. Let's now consider Q. We will represent each of the outcomes Q as a row in our figure. We will thus set the number of elements in the sample space for Q equal to 4. That is to say, we will set n equal to 4 in drawing this figure. Now, when looking at this figure and considering the probabilities of the elements of Q, you have to ignore the divisions of the rows that come from P and consider only the horizontal lines that divide up the sample space according to Q. Furthermore, in drawing these lines for the division of the sample space according to Q, I have used the fact that the two probability distributions are independent. If you want to find out more about the way these Venn diagrams can be used to represent things about probability, then I have other videos that you can look at that explain the subtleties that are at work here. For our purposes, notice that once we have divided up the sample space in this way, we now have m times n little squares. In other words, the joint probability, p times n, is a uniform distribution with m times n possible outcomes. Let me explain this another way to make it totally clear. Let's suppose I toss a coin and roll a dice. Each of these things independently generates a random answer in accordance with the uniform probability distribution. The coin gives either heads or tails, and each of these two possible outcomes has a probability of a half. The dice, meanwhile, will give either 1, 2, 3, 4, 5, or 6, and each of these outcomes will have a probability of 1/6. Doing both simultaneously, we have 12 outcomes for the experiments, 12 outcomes in the sample space. We can get heads and 1, heads and 2, and so on, or we can get tails and 1, tails and 2, and so on. Furthermore, all these various outcomes are equally likely. Let's now consider the information in this joint probability distribution. We know from our fourth property of the information functional that the information is additive. This means that the information for the joint probability distribution function must be equal to the sum of the informations for the probability distribution functions P and Q as shown here. In addition, we know from the first property of the information that the value of the information is a function of the elements of the probability distribution function. All the probability distributions here are uniform, however, and thus all the elements of the probability function are equal to 1 over the number of elements in the sample space. We must therefore have that the information for the joint probability distribution function is a function of 1 over n times m, the information for P is a function of 1 over n, and the information for Q is a function of 1 over n. We thus have from the additivity property that the information is some function f for which f of 1 over n times m is equal to the sum of f evaluated for 1 over n and f evaluated for 1 over n. The only function that satisfies this equality is the logarithm. We can thus write that for a uniform distribution, the information is given by minus k log n, where n is the number of elements in the sample space. This concludes what I wanted to discuss in this video. To summarize, we have arrived at the realization that the information for a uniform distribution with n possible outcomes is equal to minus some constant k multiplied by the logarithm of n. It is very important to remember that this result only holds for uniform distributions. When the information of non-uniform distributions is evaluated, it will always be higher than this value. The arguments in this video are a bit unusual, so please watch it again if you are confused, as we are going to use this quantity, the information, a lot in the videos that follow this one. Thank you for your attention.